Okay, this is page 37 of the complex numbers workbooklet, and we're looking at curves and regions on the Argand diagram. Now, the modulus and argument of a complex number can be defined algebraically, or we can think of them geometrically. Now, we're just looking at some examples involving algebraic definitions of complex numbers. So, for example, you may be asked to sketch the locus of Z for these following situations. For example, in each of these as well, we're going to interpret them algebraically and then we're going to sketch them. So on the Argand diagram, sketch the locus of Z for the following. Now, if we've got Z plus conjugate of Z is greater than 4, we'll let Z equal X plus YI. And so therefore, we've got that X plus YI plus X minus YI, so that is Z plus bar Z, or the conjugate of Z, is greater than 4. Now, simplifying, we get 2x is greater than 4, and so therefore x is greater than 2. So therefore, the locus of this, we're sketching the locus, so the locus is just the graph of x is greater than 2. Remember, we do not do a solid line here at x is 2. And if x is greater than 2, we're sketching this right-hand side. Okay, now these algebraic ones, they're fairly easy to do. There's no set rule with them. You're just really substituting z equals x plus yi. Now with this second example here, we want to sketch imaginary z is equal to 3. So if our complex number again is z is x plus yi, and if imaginary z is 3, and there is no real z here, then your complex number will be 0 plus 3i. And to sketch this, it would just be, because we sketch 3i, remember, is on the y-axis, so we're basically just going to be sketching the line y equals 3. Okay? So actually, you've got to be careful here. What we know is just that z is 3i. It's not the point 0, 3i. So it could be many points. It could be, we just want the imaginary part, to be 3. So it's actually the set of all points on the line y equals 3. Okay, so all along here, imaginary z is 3. It's not just the point 0, 0, 3 up here. It's the set of all points where imaginary z is 3. So the locus is all the points on the line y equals 3 in an Argand diagram. Okay, now with the next one, real z plus imaginary z is equal to 3. Now with a complex number, real z is represented by x and imaginary z is represented by y. So what we want is x plus y to equal 3. So really here we're letting real z, basically we're letting real z equal x, and we're letting imaginary z equal y. Now we could have just done that up here. Let imaginary z equal y, so therefore we get y equals 3. Okay, so let real z be x, imaginary z is y, so therefore this becomes x plus y is 3, which is the equation y equals 3 minus x. So therefore the locus here is a straight line with the equation y equals 3 minus x. Now you can either graph this by x-intercept, y-intercept. Y-intercept is 3. And when y is 0, x is 3, it's also the line with a gradient of -1 with a y-intercept of 3. So therefore that's the locus of that line. So that's the locus of this, real z plus imaginary z equals 3. Now in the next one, all right, we need to do a little bit of working out here. We've got 2 times the modulus of z is equal to z plus conjugate of z, or z bar, plus 4. Okay, now we're going to, of course, let z equal x plus yi, and the definition for modulus of z is the square root of x squared plus y squared. Okay, so therefore substituting that all in, we've got 2 times the square root of x squared plus y squared equals z plus the conjugate of z, which is minus yi, plus 4. Now collecting like terms, we've got 2 times the square root of x squared plus y squared is equal to 2x plus 4. Now we can divide through by 2, so the square root of x squared plus y squared is 2x. So dividing through by 2, we get x plus 2 because it's 2x plus 4 over 2, which is x plus 2. Now we can square both sides. So x squared plus y squared will be x plus 2 squared. So we are squaring both sides. And so x squared plus y squared is x squared plus 4x plus 4. And now collecting like terms and simplifying, we get that now the x squareds cancel, you get y squared equals 4x plus 4. Now this is y squared equals 4 bracket x plus 1. Now this is a parabola. It's of the form y minus k squared equals 4ax minus h. So this is a parabola. It is the y squared equals 4ax type, and it's of the form y minus k squared equals 4ax minus h, where, and it's actually of the, it really is y minus 0 squared equals 4 times 1, x minus negative 1. Therefore we have a sideways parabola. We've got the focal length is 1, and we've got the vertex of this parabola is 0, negative 1, and it's a sideways parabola because it's the x is y squared type, not the y equals x squared type. So we've got the vertex at 0, negative 1. Also, when x is 0, you'll get y is plus or minus 2 as well. Okay, so we can put those points in as well. So just looking at that there, might just do that here as well. When x is 0, we get y squared is 4, so y is plus or minus 2. Okay, and here's our vertex at 0, negative 1, and this is negative 2, and the focus is here at 0, 0. That's where the focus of the parabola is. So therefore, the locus of these points is a parabola with focal length 1, vertex 0, negative 1, and focus at 0, 0. Okay, so that is the locus of that. Okay, it says sketch, question 6, sketch the curve in the Argand diagram defined by this equation: imaginary z minus 1 plus 3i is equal to 4, and to find the minimum value of modulus of z subject to this condition, and state the value of z for which this minimum is obtained. Okay, once again, we'll let z equal x plus yi. That means that z minus 1 plus 3i is x plus yi minus 1 plus 3i. And collecting real and imaginary terms, we've got x minus 1 plus I times y plus 3. So therefore, the imaginary part of z minus 1 plus 3i, the imaginary part, is the y plus 3, and that imaginary part is equal to 4. So therefore, we've got the equation y equals 4 minus 3, which is 1. So therefore, the locus is the equation y equals 1. So here I've got y, x, and the equation is y equals 1. Now, in other words, your point will travel along this line, along y equals 1. So the x value could be anything, but the y value is always going to be 1. So for example, I'm just going to pick a point P on this line, but it can travel anywhere along there. P can travel here. This point here is 0, 1, for example. This is the origin. Okay, this is the length of OP. Now it says find the minimum value of the modulus of z. Now this is the modulus of z, this length here, and the minimum value will occur here. And 0, 1 on the Argand diagram represents I. okay, because it's 0, 1, y-axis is yi, remember. So therefore, if P represents your, I'll just call it complex number Z1, okay, then OP, then OP is the modulus. Sorry, if P represents Z, your complex number, not Z1, then OP represents modulus of Z. Now OP has a minimum value of 1 when P has coordinates 0, 1. Therefore, modulus of Z has a minimum value of 1 when Z equals I, because this point here on the Argand diagram is the point 0I, in other words, and therefore the modulus of Z will be I. Okay? Okay, that's that one. Now for question 7. Sketch the region in the Argand diagram defined by this. 6 is less than or equal to real 2 minus 3i times Z, which is less than 12. And also, so it's a union of two regions, and real Z times imaginary Z is greater than or equal to 0. Okay, so that will define the quadrant that we're in. So for real Z times imaginary Z to be greater than 0, you've got to either be in quadrants 1 or 3, because a positive times a positive is positive, and a negative times a negative is positive as well. So again, letting Z equal x plus yi, therefore 2 minus 3i times Z will be 2 minus 3i times x plus yi, which is 2x plus 2yi minus 3xi minus 3yi squared, which is 2x, collecting, this will be 2x plus 3y, plus I is a common factor between these two, 2y minus 3x. So therefore the real part of this, the real part of 2 minus 3i times Z is the real part of this, which is 2x plus 3y. So therefore we want 6 to be less than or equal to the real part of 2 minus 3i times Z, which is less than 12. So therefore this is the same as sketching 6 is less than or equal to 2x plus y, which is less than 12. So we need to consider two equations. And those equations are this: 6 equals 2x plus y and 2x plus y equals 12. With the less than and the less than or equal to, we'll do our shading then. This just means that this is going to be a solid line for this graph, and this one, this graph here, 2x plus y equals 12, is going to be the dotted graph. Now I'm going to draw the graph down here. Now I'm just going to do it with x and y intercept. So when x is 0 for this graph, so for this first graph, when x is 0, y will be, sorry, I think I've not written this out right. Just one sec. I've got 2x plus 3y, sorry, so that's 2x plus 3y, 2x plus 3y, 2x plus 3y, 2x plus 3y. So sorry about that, I've just transcribed that incorrectly here. So therefore, when x is 0, y will be 2. And when y is 0, x is 3. So for this graph, when x is 0, y is 2. When y is 0, x is 3. This is the solid line graph. So I'm going to draw that there. I'll just continue it there. And for this graph here, when x is 0, y is 4. And when y is 0, x is 6. So x is 6, y is 4 up here, and this is the dotted line. Now remember, we also want real Z times imaginary Z being so greater than 0 or equal to 0. So if real Z times imaginary Z is greater than or equal to 0, we're saying letting real Z be x. and letting imaginary z be y, that's got to be greater than 0. That will only occur here in quadrant 1 because there's no quadrant 3 for this graph. So therefore we're only in quadrant 1, so we don't really need these extra bits of the graph here. Okay, so we're interested here in this quadrant. Now let's look at our shading. So we're considering two equations. 6 is less than or equal to 2x plus 3y. So let's consider a point in the middle. If this is 3, 0, I'm going to try the point, say 3, 1. I definitely know that that lies in between these two regions. The other thing is I can try 0, 0 down here. And 6 is not less than, if I substitute in 0, 0, I get on the right hand side 0. 6 is not less than 0, 0. So the shading should be up here, but I'll just double check with 3, 1. When x is 3 and y is 1, I get 6 plus 3 is 9 on this side. Yes, 9 is greater than 6. Now with this equation here, 2x plus 3y is less than 12. I'm just going to try this point 3, 1 again. X is 3, y is 1. When x is 3, I get 6 plus y is 1. I get 6 plus 3 is 9. 9 is less than 12. So therefore the shading will be on this side. So therefore this is the region that's being shaded that is defined by those two statements up there. Real, this statement here, and real z times imaginary z being greater than or equal to 0. So that's our solution there for question 7 on page 38. This is question 5. Sorry, the solution's already written out because it was recorded and then something went wrong with the recording. So we're doing this question 5. So the modulus of z squared minus the conjugate of z squared, the modulus of all of that, is less than or equal to 4. Now we're going to do this algebraically. If we let z equal x plus yi, which we're going to do down here, but if we look at this, this is z squared. This is of the format a squared minus b squared. So we're going to, if this is a squared minus b squared, we do a minus b, a plus b. So z minus z bar times z plus z bar. We're then going to substitute z equals x plus yi in. We get x plus yi minus x minus yi times x plus yi plus x minus yi. Collecting like terms in each set of brackets, we get 2yi times 2x. And we get 4xyi. So therefore the original question is that. So z squared minus the conjugate of z squared, modulus of all of that, is less than or equal to 4. Can be replaced with the modulus of 4xyi is less than or equal to 4. Look, we can divide both of these by 4 because that 4 is positive. So the modulus of xyi is less than or equal to 1. Now to do this is a imaginary part. There is no real part to this. So that's the same as doing the modulus of 0 plus xyi, the modulus of that, 0 plus xyi. Now remembering the definition of modulus of z is x squared plus y squared. So we do 0 squared plus xy squared, which is going to be xy squared. Now, looking at this, we've got two cases here, even if you just look at the absolute value. This is saying, absolute value, if xy is positive, this just remains as is. So if xy is positive, the modulus of xyi will equal just xy. That's because x times y is positive. So therefore this will become, because we know that the modulus of xyi is square root of xy squared. Now that will equal xy or minus xy, just depending, using definition of absolute value. That's what I mean by the xy bit. It could be positive xy or minus xy depending on the values of x and y. So modulus of xyi will just equal xy if xy is positive. So therefore this equation becomes xy is less than or equal to 1. Now this is really a hyperbola. So I'm going to sketch y equals 1 on x. I'm not going to write it as y is less than or equal to 1 on x. I'm just going to write y equals 1 on x, which is quadrants 1 and 3. And then I'm going to substitute in points for xy to see where my shading in quadrants 1 and 3 occurs. Okay, so if you rearrange this and write y is less than or equal to 1 on x, then that could be correct for one quadrant but incorrect for the other. We know that as stands, x times y has to be less than or equal to 1. So just doing some points here, I know that that's the point 1, 1. And this, for example, is the point -1, -1. So I'm just going to pick the point, for example, a half-half. Or even, a half-half in this quadrant and negative a half-half. negative a half in this quadrant, and I'm going to see where my shading will go. So if x is a half and y is a half, we get a half times a half is a quarter. Is that less than or equal to 1? Yes, it is. So I shade in here. In this quadrant here, if I choose the point negative a half times negative a half is a positive a quarter. That is less than 1. So I shade in here. So that's quadrants 1 and 3 taken care of. Now, for my second case here, like for example, absolute value of xy. Now, if xy happens to be negative, then of course, when you take absolute value of something, you get a positive answer. So if x and y happen to be negative, then you have to do the negative of the negative to get the positive answer. So if xy is negative, then we get that negative xy, negative, and xy itself will be negative. So negative will be less than or equal to 1. Okay? This is from the following definitions of absolute value. I'll just do it up here. Absolute value of x is equal to x if x is greater than 0, and it equals negative x if x is less than 0. Because, for example, if x is, say, negative 2, you get the negative of negative 2 is positive 2. Now, that's what we're doing here. So, if xy is less than 0, then actually I should put one extra line here. I'll just rub that out. Then the modulus of xyi will equal negative xy, which means that negative xy is less than or equal to 1. Swapping sides, we get xy is greater than or equal to negative 1. Sorry, you just can't see that very well. I'll do that again. So we get xy is greater than or equal to negative 1. So we need to sketch again y equals negative 1 on x. So I'm going to sketch y equals negative 1 on x. That's quadrants 2 and 4. So that's what I sketch, but this is what I test up here. I don't go and rearrange this and put y is greater than or equal to negative 1 on x, otherwise I'm going to get incorrect results. So here I'm going to do the point negative a half, positive a half in here. I want to see if the shading's in here. So negative a half, positive half will give me negative a quarter. Now, yes, that is greater than negative 1, so I shade in here. Remember, a point here might be negative 1, positive 1. A point here would be 1, negative 1. I'm going to choose a point in here, which would be a half, negative a half. So a half times negative a half is a quarter, is negative a quarter. That is greater than or equal to negative 1. So again, I shade in here. So therefore, sketching the locus of Z will be the hyperbolas y equals 1 on x and the hyperbola y equals negative 1 on x. So we're in all 4 quadrants, and considering each quadrant individually with xy is less than or equal to 1 and xy is greater than or equal to negative 1, the shading occurs inside, like between the asymptotes and the graph. Okay? And that's the end of that question there.